question. Okay, so we're going to talk about interference of waves. So let's say we have a string. And let's say we grab the left end and create a pulse that travels down the string that looks like this. Let's say at the same time someone grabbed the other end and created a pulse that looked like this. You know, I'm going to draw it a different color. I'll draw both of them different colors. So here we have pulse 1 that looks like this, and pulse 2 that looks like this. And they're moving, oh, they're going to be moving the same speed. I should probably use the same color for that, but whatever. So again, if you look at a later time, you know, they're getting closer and closer together, but at some point they're going to overlap. And what's going to happen while they overlap? And that's what we call interference of waves. So there's no point in drawing anything until they start to overlap. So let's say this pulse 1 is going to look like this. And pulse 2 is going to look like this. Now, I'm just going to leave this kind of like a reference line. We'll just leave it. Okay, so we've got these two waves. They're moving in opposite directions. But at one moment in time, if these two pulses existed independently, now they'd overlap like this, but we only have one string. So what's the actual string going to look like? And the answer is given by something called linear superposition. So it's kind of like a big word, but actually the concept is fairly simple. Let's call this our x-axis, and let's call this our y-axis. So y is the amplitude of the wave. So here, let's call this wave 1. And this one here is wave 2. And so at any given x value, let's say just y is the amplitude of what the actual string would look like. That would be y1 at that location plus y2 at that. So again, we have to look at a particular x value, and then we would just add the two y values. So let's pick up an x value, say here. What would the actual string look like? Well, y1, the amplitude is right here. And y2, the amplitude is still 0 because that pulse hasn't reached that point yet. So the string going from the left would look like this until we reach this point, or until we cross this point, and then we have this interference going on, where the two waves are overlapping. So let's look at this x value, for instance. We have one y value. The amplitude of this red wave is, from y equals 0 to this point, and we'd have to add to it this amplitude. So the actual wave would look, the actual string would reach up to this point here. So the actual string, it would follow this red one, and then it'll come up here. And again, by this point here, we have to match the blue string again. And so the black line would kind of look like what the actual string would look like. So linear superposition, kind of a big word, but this is all it is. At each x value, you add the amplitude of the individual waves that are interfering with each other. And again, we could do this as well. We could have y3, y4, whatever. You can add any number of waves this way. Okay. Now I said in principle, this is very simple. In practice, this could be very difficult. We could end up with a problem like this, whereas let's say we have two sine waves crossing. We could have like the amplitude, where y1 would be, say, like a1 sine of, well, we're looking at one moment in time, so we'd have, say, 2 pi over lambda 1x. And the other one would be described by a sine wave as well. Except this one would maybe be shifted. Let's do this. I'll just throw that. So again, this could be your result. Not a very clean result. And don't worry, we're not going to be doing things like this. So you don't have to worry about that. But the principle should be clear enough. We can illustrate that by looking at the somewhat unrealistic example, what we call square waves. Where, say we have a wave that looks like this. Now, is this a realistic wave? Not entirely. Waves generally don't have sharp corners like this. Interestingly enough, though, in electronics, you can create waves that they're called square waves, and they do look like they just have like, you could have something like this. You can actually create waves that look just like this. Now, technically, they don't have perfect 90-degree angles, but yeah, those are something that you can create in practice, where to a very good approximation, they are square waves. Anyways, so like if we have, say this is wave 1, and wave 2 I'll make in red. Here, let's say that this is x equals 0, and here's x equals 1, 2, 3, 4, and 5. So like here, the amplitude, let's say this is 1, these are 2, that's 0, that's negative 1. So if wave 2 looks like this, we can add these two waves. So, and again, this is simple because they're nice, horizontal lines we're adding up. So the amplitude here is 1. And let's say the amplitude of this red one is negative 2. Like over in this section. Now in this next interval from 1 to 2, this is 2. The red one's also negative 2. And then from 2 to 3, we have 2 and 0. And then for these two segments, that's 1 and 1. The black wave is 0 and negative 1. So if we just look at this interval from 0 to 1, we're adding 1 and negative 2. The result is going to be negative 1. I use blue for the resulting wave. And now here, from 1 to 2, the amplitudes are 2 and negative 2. They cancel out there. So this would just be flat at that point. And then from 2 to 3, we're adding 2 and 0. So we go up to here. And then, for this next interval, it's 1 and 0. So the amplitude is 1. And finally, 1 and negative 1, that's 0. So basically, what we have here is black plus red equals blue. Now, dealing with more realistic waves that are described by things like sine waves, the principle is exactly the same, just the details are much more complicated. But we're not going to really have to worry about that. Now, so interference waves, very important topic. So again, just the principle of linear superposition. You just go through each x value and add the y values to get the amplitude of the resultant wave. Now, let's look at an example involving sine waves. Actually, before that, we look at, say, an extreme example, two kind of extreme examples. So let's say we have these two identical waves moving towards each other. And at one point, they're going to completely overlap. And when that happens, the amplitude will look just like these waves, but they'll be twice as big. And so when that happens, we say this is constructive interference. Now, another example, let's say we have this wave and this wave. They're identical, except one of them is upside down relative to the other, and at some moment these two are going to perfectly overlap, and then the result, if this was like a wave on a string, the string for that one moment in time would be perfectly flat. And this is called destructive interference. So yeah, if this was a wave on a string, it would be totally flat. If this was a sound wave, what would happen is, remarkably, you wouldn't hear anything. If you got those waves to perfectly cancel out, there would be no sound. Now, again, it's difficult to do this in practice because that was just one moment in time. We kind of picture both waves still existing, except they cancel each other out. But then afterwards, what's eventually going to happen is this wave is going to keep moving to the right, this one's going to keep moving to the left, and they'll lose that perfect cancellation. So if we just had these two pulses, they'd only cancel out for a very brief moment. And so, to get it to cancel out in a more permanent way, we have to kind of rig up a special situation where that would occur. But that's called destructive interference. And again, another example, the same interference applies to light as well. So you can have a situation where you have two lights, like you have one source of light and an observer sees something, and then you can turn on a second light and the observer won't see it anymore because it won't see any light, it's gone dark at that spot. And so, it's really interesting that you can actually turn on a light and make it darker, at least in one location. And so, it would actually get darker as a result of that second light being turned on. Now, just to be perfectly clear, you're never going to see this in practice. Like, say you have two lamps in a room, and you turn one on, and then you go over, turn the other one on. The room's always going to get brighter. It's not going to suddenly get dark. And that's because the light coming from a typical light bulb is very random. You've got, different types of light, different frequencies and different wavelengths, and they're being emitted from the light bulb in a kind of random way. So maybe at certain locations, two waves would pass by and temporarily cancel each other out at one location. But again, there's going to be so many waves in that area, you're never going to get cancellation on a large scale. This kind of destructive interference, you can see it with light, but you have to set up a situation where it's not only going to happen, but it's going to happen in a noticeable and sustained way. It's not going to be like a temporary thing. Because, like, say two waves pass by and cancel out. Well, you wouldn't even notice that because there's a lot of waves coming from all directions. And, like, if you just look at, say, like the tip of this marker, like that area of the room, there's a lot of light waves bouncing around. And so if a few happen to cancel out, the rest of them aren't going to. So you'll never even see a portion of a room just suddenly go dark. But you can create a situation where it will at one point. We'll talk about how we could do that in a minute. But yeah, the basic idea, constructive is when they overlap, destructive is when they cancel each other out. We're going to stick mostly to sound waves here. And let's look at an example. Say we have two speakers, S1 and S2. And let's say that we have an observer here. Now, very importantly, we're going to say these speakers are producing sound at a pure tone. So again, you have this membrane, and you can, drive it. I think most speakers use like magnets. You can drive it with magnets, and so you can have it kind of oscillate back and forth. And that's going to, if you just have this membrane oscillating back and forth at a particular frequency, you're going to produce sound of a particular frequency. And so we're going to say that both of these are producing, we call that a pure tone. And if you plot the sound wave, it would look just like a sine wave. Now, of course, the sounds you typically hear don't look like this. They're much more complicated. But if we produce a pure tone, it's going to look something like this. And so both speakers are producing a pure tone. And we're going to say that the two speakers are in phase. So what that means is, say we have both speakers. And let's say we push the membrane so it does this. It goes from flat to doing this, where it's going to compress the air, and that compression wave will move outwards. The second speaker is going to do the same thing at the same time. And then when this one moves this way, this one's also going to move this way. So they're going to be moving back and forth together, and we say that they are in phase with respect to each other. Now, if you just had two separate speakers connected to different power supplies, and then say turned one on and then randomly turned on the other, they would not be in phase. And so we have to make sure that we're running them in a way that they're being driven in phase so that they're doing this. And that's all we're going to do in this class. We're always going to consider the speakers to be in phase. But it's important to understand that, that's not always going to be the case. Just the cases that we're going to consider because it's much easier. If you want to challenge yourself, there's a problem, not a problem for you to work out, but I went over an example where two speakers were not in phase. So it's a good test your understanding if you can follow that example. But you won't be required to do problems like that. Okay, so the question is, what is the observer going to see? How would we answer that question? Actually, I could have probably left this picture here, but first I'm going to write this equation. The speed of sound is the frequency times the wavelength. And let's draw this line here. Let's call that D1, the distance from the observer to source 1, where that's the closer speaker. And then from the observer to source 2, we'll call that D2. And what we're going to do is we're going to draw a circular arc here. Why do we do that? Well, if this is the arc of a circle, then this distance here, from here to here, is going to be D1. And this distance from the observer to the source, that's D2. So we've got this, because S2 is farther, we have this extra distance, which we're going to call delta. And it's very easy to see that, just going from the observer to the source, for example, d1 plus delta equals d2. Just going from the observer to the source, here we can see it's d1 plus delta, or here it's just d2. And so delta equals d2 minus d1. So delta is the difference in the distances between the two sources and the observer. And for that reason, it's called the path length difference. So let me kind of redraw this picture here. We have S1. Here we have our observer. Here we have S2. And that distance is called delta. So what I want to do, I'm going to erase this picture. We have all the essential information over there. Let's look at from S1 to the observer. So let's say this is S1. The observer is way down here. And just for convenience, let's use a nice sine wave. We don't have to go all the way to the observer. It's just going to keep on going. And so when we hit the observer, this wave is going to have a certain amplitude. Okay, so that's from S1 to the observer. Now S2 is going to start farther away. So if we go from the observer, S2 is going to be somewhere over here. Where this distance here is delta. So we're going to draw S2. Remember, we start out in phase. So we start this wave the same way we started this one. And it's an identical wave because they have the same frequency, which means they're going to have the same wavelength. And so the question is, what is the observer going to see? And I want to write down the conditions that we would need to see constructive or destructive interference. So what would delta have to equal to give us destructive, or let's start with constructive interference. And this one, it turns out, let's say, for constructive interference, delta equals 0 will work. If you have, say, two, like say they're both the same distance from this line. So just, we can see that these two distances are the same. If delta is 0, S1 and S2 are going to overlap, and these waves are always going to overlap. So delta equals 0. If they start out with the same amplitude, they're going to end up with the same, whatever the amplitude is at O, at the location of the observer, these two waves are going to perfectly overlap, and so we will get constructive interference. That's not the only way we're going to get constructive interference, though. What if delta is equal to a full wavelength? So a wavelength is this distance. So I'm going to go back, and I'm going to place S2 here. So close enough. And so let's say S2, I'll use a different color. S2 is going to go through one full wavelength, and then we can go the rest of the way, and we can see that they're going to continue to overlap. They're identical waves. So if we go through a full wavelength, then we'll just keep following this curve, and they're going to be in phase when they reach the observer. So if delta is equal to a wave, if it's equal to 0, we get constructive interference. If it's equal to a wavelength, similarly, if we let delta equal 2 wavelengths, Again, we can just add a wave to the left, but then it's going to repeat itself. So adding a full wave does not change the phase at the end. So 2 lambda and so on. We can say 3 lambda, 4 lambda, doesn't matter. Yeah, so these are the conditions that will give us constructive interference. Now, let's look at destructive interference. I'm going to erase this. Try to redraw what we had. So that's S1. Now, how would we get destructive interference? Now, we want it, so like say the observer is right here. We can see that this wave is up here. We want the other one to be just beneath it so they cancel each other out. And so I'm just going to write down the condition, and then it should be clear why this is the case. Let's say delta is 1/2 of a wavelength. So this is half of a wavelength. So if I write S2 here, yeah, it's going to go like this. And we can see that these two waves are completely out of phase. You know, you look at NEX, you know, when this one's high, the other one's low. When this one's, you know, low, the other's high. They're always directly opposite each other. So when they reach the observer, they're going to cancel each other out. So delta equals half a wavelength will give us destructive interference. Similarly, if we add a full wavelength to this, again, that doesn't change anything. You just add a full cycle and then you're back to where you started. So another possibility would be 3/2 lambda. Just add 1, 1/2 plus 1. And then 5/2 lambda. And so on. So overall, the conditions for constructive, we can combine this into one simple formula. Where, yeah, I wrote the condition for destructive interference on top and constructive interference below it. And M can take any of these, 0 or any positive integer. So those will give you, again, like if you plug M equals 0, we have 1/2 lambda for destructive or 0 for constructive. So we get these two numbers. If M equals 1, we have 3/2 lambda or 1 lambda. So that's, the next one. And then if M equals 2, we'll get 5/2 and 2 lambda. So that kind of tells you what type of interference you're going to, that tells you where you're going to get constructive or destructive interference. Now in general, you're not getting either of those. Like if delta is 1/4 of a wavelength, they'll meet not perfectly in phase or perfectly out of phase. It'll be somewhere in the middle. And so we want to look at like kind of pure constructive or pure destructive interference, and those are the conditions. Okay, so basically we'll do some examples, but what you want to do is you want to look at delta based on, like, that's going to be based on geometry. Like for a given problem, you'll have two speakers, say S1 and S2. The observer is going to be somewhere. And again, you want to find the distance from S1 to O and S2 to O and just take the difference, and that's delta. So again, finding delta, the actual path length difference, is typically like a geometry problem. And then you compare that to the wavelength. Now we're usually talking about sound waves here. So the wavelength would be the speed of sound over the frequency. So the speed of sound is just a given, 343 meters per second, unless told otherwise. And then you divide that by the frequency of the sound, which is typically something known. So delta is a geometry problem, and then calculate the wavelength, which is usually fairly simple, and then just compare them. And that'll tell you if you get destructive or constructive interference. Okay. I think we got a few more kind of random topics to talk about. There's a few examples. We're going to go over those in class, like during the review. So I want to look at another topic. This is a good place to. This has been 30 minutes. That's a good length for a video. So we've got, I think, 2 more topics to talk about. And I'll put those on one other video. I'll just combine those. So this is the fundamentals of this chapter. This is a good place to stop. And then we'll kind of build off this to talk about the next topic, which is diffraction.